Before watching the video, do subscribe my channel and hit the bell notification icon to get the instant updates. Now I'll discuss a few questions which will help you to understand the concept of Fischer projection along with the tetrahedral wedge and dash representation. Okay, so in the first case, how many optical centers do you see? Just one, and that's the second carbon. Now, to represent in Fischer, I had given a simple rule: angle on the right, solid wedge on the right. So, if the representation is like this, just try to convert the representation in such a way that the angle which you are getting between the bonds related with the chiral carbon either to the left or to the right. So, if I rotate this molecule by 90 degree, what I'll get the chain of carbon like this. You can visualize the carbon 1, 2, 3, 1, 2, 3, 4 as this. So now the solid wedge, the Cl, would come on the right side. So the fourth valency, which is behind and is hidden, is H. Once you identify like this, just look at the angle between the bonds, this and this. You can't see any angle, you have to see the angle associated with the chiral carbon between the straight lines. Now, in Fischer projection, rule is if the angle is on the left, the solid wedge is on the left. Cl comes here, so its opposite would be H. The above part is methyl and the below part is entirely CH2, CH3, which is ethyl. So that's 2-chlorobutane converted into the required Fischer projection. Now look at the second example. In second example, I can see two optical centers or chiral centers. So that's carbon number 2 and carbon number 3. Visualize the chain of carbon as this in the form of a C shape or board shape. So again, just by convention, you rotate in the clockwise. Either ways you can do, but convention हम ये follow करेंगे that we will rotate it by 90 degree on the right side or clockwise direction. So I'll get the board shape now like this. Now the Br will come on the right, so the hidden valency H on the left. Same way में the dashed OH, and now the hidden would be H. Correct? So now, in this case, there are two chiral carbons, that's why the Fischer projection will look like this, two intersections. On the second carbon, you can see the angle between the straight lines going on the left, solid wedge on the left. Third carbon, again the angle is going on the left, solid wedge on the left. That's H over here. Now Br ke opposite we have H, H ke opposite we have OH. The above part is methyl, below is methyl. That's Fischer projection for the second one. Third one, again two chiral centers can be visualized, and I can take the chain of the carbon as this, and again just try to rotate by 90 degree in the clockwise as convention. So if I rotate, I'll get the chain like this. Yeah, and now the SH, the thiol group, would come on to the left, the Cl will come on the right. So the hidden valency over here is H behind, and here the H in front. So now converting this to Fischer, here the angle between the straight lines is on the right, so solid wedge on the right, the thiol group, THIOL, and the H would be on the left. Here the angle is now onto the left, so the solid wedge H would come on the left, Cl here, this is CH3 and this is CH3. That's Fischer projection for the third one. Is it clear? Also, when we talk about carbohydrates, with a simple example of glucose and fructose, even they are found to be optically active. We know that glucose is having a formula C6H12O6, and it's an aldehyde compound with an aldehyde group at the top with 4 chiral carbon, meaning Fischer projection 4 intersections, and ending with CH2OH. The 4 carbon atoms in the middle are satisfied with H and the hydroxy group, and the arrangement is H-OH. The third carbon has OH on the left and H on the right, and the other H-OH, H-OH. So that's the representation for glucose, the aldose. Also, one more thing, the number of optical isomers which we can get for a given optically active compound is equal to 2 raised to n, where n is the number of chiral centers or chiral carbon atom. In the first case, since I had 1 chiral carbon, the isomers would be 2, and we know that one of them will be dextro, other would be levo. In second case, since I have 2 chiral centers, the total isomers would be 4. One of them will have this representation. Second would be its mirror image. Third, when you swap the valencies OH and H, and fourth will be after swapping the mirror image. So that would be 4 possible structures of this 2 chiral center compound. Third one, same 2 centers, so 4 optical isomers. In case of glucose, I have 4 chiral centers, there will be 16 possible isomers, out of which the 8 will have different arrangements with respect to the chiral center, and the other 8 will be their mirror images. Since the structures have different optical properties, they are also given their different names. Like glucose is this representation, there can be telos, mannose, and so on. So for glucose, the arrangement is this, and the natural form of glucose is basically dextrorotatory. So the glucose is also called dextrose, and that's why glucon D actually has the representation of capital D as dextrose. Glucose and fructose were having the same formula, so they are isomers of each other, but glucose and fructose have the different functional group. Glucose has an aldehyde, fructose has a ketone, so they are not stereoisomers, they are structural में functional isomers. What are they? They are functional isomers, not stereoisomers. So fructose has alcoholic group at the start, ketone at the second non-terminal position. It can't be at the terminal, right? Then the 3 carbons with chirality, and the last one satisfied with CH2OH. Even the fructose ka third carbon has the arrangement of OH on the left and H on the right. Rest have H and OH as left and right respectively. If you see, the last 4 carbon of glucose and fructose have similar arrangement. The difference is in the first and the second. And with the 3 chiral carbons, the number of optical isomers for fructose are 8. So there will be 4 different arrangements and their corresponding mirror images.